Okay, so you've seen the theory and you've seen the video on definitions of F, point of application of F, line of F, or line of action, it's called, R perpendicular, the lever arm, moment arm, the line of R, and which I suppose I said, and F perpendicular, which is the tangential component of F. Doesn't care about fx, fy. It might be fx, it might be fy, but it's the part of f that's going around, the tangential component. So you've seen how to do that. You've seen how to choose plus and minus however you want. Often it's counterclockwise plus, but it doesn't have to be. And you've also seen how to use the vector cross product to find torque. Let's do some examples. All right, cool. So the method, just have a clear method. Start from the beginning. So if you know you're going to do the method, lay out the general method, get specific. General to specific. So the general problem for torque analysis, the general setup is that you summarize or you sum up excuse me, the torque from each force around some chosen axis, axis of rotation, origin, however you want to call it, on the object that you're looking at. There's the rotational inertia, moment of inertia of that object, but this has to be around that same axis. And the angular acceleration of that thing around the same axis, and usually it's some sensible axis like the axle of a wheel or spinning disc. Now, we're going to look at static equilibrium. So equilibrium means alpha is 0, and so I have this nicely written. I'm going to get rid of that. And it's the same basic idea. If acceleration is not 0, you're still adding up the torques from each force. If acceleration is 0, then that makes life easy. Sometimes that'll solve a lot of your problems. This is a new idea, so a little clue here is that a lot of problems can just be solved there. So I would start there. Now, if you've got more unknowns, usually 3, one unknown for that equation, another unknown for this one, another unknown there, then you know that you're going to do force analysis if needed. Usually in problems of beams and ladders and such, we use vertical and horizontal as the axes. Makes sense, doesn't it? So, let me just get this going for that. So then we take some of the forces. Again, same forces. So this is a key idea here. There's forces, these are all the same forces. We look at the torque that they provide around an axis of rotation. Right? Here we look at just the component of the force in the x direction, causes max. The component in the y direction, or vertically usually, causes may. If it's equilibrium, it's still the same game, but it's set at equal to 0. So just realize it's the same. Every force could have a torque, could have an fx, could have a fy. All right. Of course, there's kinematics involved, so if you do let it accelerate, or it could be moving, right? Equilibrium, there can be dynamic equilibrium. So remember, it could be moving. So then rotationally, we talk about delta theta, omega alpha, as you know. If it's static, then we say omega is 0. So static, equilibrium, rotationally, translationally, static, equilibrium, and we've got that. All right, so that's pretty easy once you get used to it. And let's have a method to do it, and then one by one do it. And then the issue is going to be isolated to some geometry and things like that. So let's go over here to the method of analysis. And the method of analysis you've done before. It's just the old free body diagram, and since it's new, we often forget, we think that it's going to be something new. But you've done this before, free body diagram. Select the object that you're interested in, maybe the rod, maybe the ladder, whatever it is, person, an arm. That'll work too. Sketch in all the forces on that thing, force vectors, right? Notice the direction. Choose an axis of rotation, select it, show it on your picture. Where is it? You can choose anywhere, just like you can choose any coordinates. You can choose counterclockwise positive, clockwise negative, or vice versa. So that's up to you. Just show it. When needed, you've got vertical and horizontal, usually. And so the key here will be one by one, get expressions for each torque from each force around that axis of rotation on that object. course. And a table can really help. It just makes you go faster because you're taking small baby steps and you go faster and you don't trip, okay? So if I look and I say, okay, what are the forces on R? Let me just list them. Bam, 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 okay? You know, gravity, tension, whatever it is. Usually it's gravity, tension, maybe a hinge, something like that. Then for each of these forces, what I need to do is look at the torque from that force around whatever axis I'm showing on my picture. So I use my method, get the torque. I use R perpendicular F, plus or minus RF perpendicular, plus or minus RF sine alpha, whatever you want to call that angle. And then what do? You add up all those expressions, set it equal to 0, solve for your unknowns. If you need to, then for those very same forces, you can break them into horizontal and vertical components. And again, sum those up to 0 for static equilibrium, sum those up to 0. The rest is algebra. So what's the tricky part? What do students stumble on and have trouble with? Two things. One is there's so many little details here that they lose sight of the big picture. And so if you just start laying out the big picture, you do this, choose the object, do all that stuff, go like that, you're at least halfway there. Now, what's the next problem? So the second difficulty is simply getting the torque from each force. Once you've done that, you're algebra land. Okay, so let's take a look. We've got a variety of possibilities. So one thing that we often do are rods. They can be these beams here, and we can, think about the free body diagram. What are the forces on this rod? Well, let's see, I've got the force of gravity on every single piece. Where should I draw the force of gravity? That can be all represented as the force vector at wherever the center mass is. Now I could balance it and find that center mass. I'll just say it's here, whatever, it could be here. M of the rod or the stick, G, vertically down. Don't twist that, right? I've seen that too. MG that way, it's like, whoa, that's an interesting little day that we're having. So MG down, right? Great. Then what else? Well, what's touching it? Well, the string's touching it. So, okay, so there's a force of tension from the string. But you don't need to do that because the force of tension in the string is the same on that end as it is here. And the force of tension in the string is equal to the mg of this object, this yo-yo. So I can just say that this is being pulled by mg, even though the force of gravity is, of course, this weird non-contact force. String is touching force. And yes, this is the string, but it is equal in strength to mass of this times g down there. Fine. So I got that. What else have I got? Well, I could do various things. Like I can pull here. I don't know if this is pretty small, pretty faint, but I can pull here on the rod, right? And I could pull at different angles. So if you want to be evil, I could just make angles. And what's the difference? Well, just draw the angles. You've got to be given enough information. So take it slower, draw clear pictures. Don't draw 45-degree angles unless they are 45, right? So I could pull there. I could go down here, or I could often, mount it horizontally to something. And so then it's got a tension. In this case, I'd have two tensions, 2T, because I've got two sides, but usually we'll just have something like that. Okay. So you've got that. You can attach a string across there or wherever. And so just draw the free body diagram, take them one by one. What else is there? Well, there's this hinge. Now, hinges are complicated, actually. So if you were to grab an object, pause the video, draw a free body diagram for that. Draw a free body diagram for that. Pause. And now you're back. What did it look like? Well, a lot of times what people draw is this. Let's come over here. Here's the rod. Oh yeah, center of mass. So that's the mass of the rod, G. And then there's my hand. Well, if that's down, clearly my hand force is going up, or my hinge force, right? That's wrong. Well, why is it wrong? Well, the force is balanced. I got up and down, should add to 0, and it does. You can see this not accelerating. Well, let me try this out. If I choose that as my axis of rotation, what's the torque for my hand? Well, wait a minute. The line of force of my hand goes through that axis of rotation. There's no torque. I'm not going around at all. So there's zero torque there. Well, that's nice and easy. But wait a minute. This torque's just carry it around. I know it's going straight down, but imagine carrying it around. If that was the only force, it would twist, and allowed to twist here, it would go this way. That's not zero. So these can't add up to zero, and yet you see that alpha is zero. Something's wrong. Now you could choose this axis and prove to yourself, hey, that's torquing that way. This has no torque whatsoever now. Or you could do this one. And you say, hey, this one's torquing around that way. This one's going that way. Can that work? That's looking kind of good. But the other ones didn't work. Huh. Interesting. Okay, so what's going on? Consider that point. Well, let's think physically. Slow it down. What am I really doing with my hand? Really, I'm doing this. If I can do it. I'm pushing up with my thumb and down over here. It's like a teeter-totter, isn't it? Up with my thumb, down here, and down here with mg. So I got a torque this way from the mg on the stick, and I got a torque the other way from my finger. So often my point is, when you stick a rod into a building or something that's holding it, really there's a force couple, we often say, or forces, one here on the edge going up, one here going down. Nonetheless, we often model that as a hinge, sort of a pin like this. And maybe it's more complicated than we've drawn. Maybe it's up and down like that. We draw it like this, and so frequently what we're going to do at a hinge point is to, so then we get into some real engineering here, some real world. But frequently at a hinge point, what we're going to do is have some HX, is often called hinge X, and HY. Now sometimes you can figure out whether or not the force is pushing it away from the wall or pulling it back to the wall, pushing it up or pushing down. Okay, so but then you just, once you've done that, so you see we're still way up here, once you've done that, that can be a little tricky, you can get past that, then you're good to go. You just break it down, choose your axis, and go. All right, so back over here to our physical example, and we see we've got kind of our mount here, our support, our hinge, if you will, right there. So I'd have to model that, and usually I'd model that as a vertical and a horizontal component separately. Sure, hinge would be hx squared plus hy squared square root, whatever, but we usually break it down, okay? So that's a little tip. Now, what happens if I do this? Well, then there's another force. So you can imagine, now watch this, I've set it up. Oh, it's accelerating. And then it's going to accelerate differently, and it's going to be really tricky to do. It's usually upper division. So what I can do is crank this down right here and see if I can manage to balance those torques just barely. Okay, I've got static equilibrium again. Do. Put them wherever, draw your thing. So, I don't know, let's just do this guy. There it is, let's model it, let's just set it up. So pause and see how fast you can do. Imagine a tension this way, hinge, force of gravity effectively, and force of gravity somewhere. Let's do it different than here. Well, that's fine, let's just do it right there. Okay, pause and draw it, see how far you can get filling out your table. All right, back you are. So let's do our picture. I'm going to model this. I'm going to do my steps, select my thing. So I'm going to draw a picture here. Now, a free body diagram, we often draw the object without anything else, but it's not bad to draw the wall and kind of imagine a hinge. Okay, there's no wall in our thing, but rod, that's fine. And then I've got my object, which is this beam or rod. Now that could be up, right? It could also be horizontal. It could be down, held by whatever. So you just do it. Just take it one by one. I'm going to try not to draw 45 degrees. That looks less than 45. So it's somewhere in here. Nice and big. Use some paper. I know. Use recycled paper. All right, fine. And we've got that. That's it. Now, what are the forces on this guy? All right, I've got somewhere. Now, this isn't exactly at the end. I might model it as the end. Maybe I'll attach it at the end. I'm going to go like this. I'm going to go lowercase m, g, and that's for my yo-yo, and y. And then I've got the force of gravity from, or on the rod at the center of mass of the rod, wherever that is. If it's even, it's at the center. If it's not even, you got to find a way to find out. So the mass, I'm going to use a capital M just so it's easy visually to make a distinction. And what else have I got? I've got a string. Now, if I wanted to be mean, and maybe I should be for this example, I can make that string not horizontal. It gets a little trickier. Let's just pull that string up over here. All right. And really the tension is not the length in the string, it's the strength of the pull. T. And I don't know what that angle is. I'm going to call that guy whatever, phi. And I'll need another angle. I can call this angle here theta, say. So now we get into a little geometry. Let's slow it down because you know the physics. The torques add to 0. If you need, the force x add to 0 and the force y add to 0. Am I missing any forces? Sure I am, right? Something going on at that hinge. So what do? Well, I just stick it in there and I go, all right, I got the hinge here. Got my, now that's being pulled that way, so I think that this is going to push that way, hx. Now you can draw it with the tail. We often do that, right? Here, hx. And these guys are pulling down, but that's pulling up, but I'm going to guess that they're pulling down more than the tension's pulling up, so I'm going to go hy, really is here. I mean, you can do it off to the side. You're just representing how strong. And now I've done my free body diagram. So I had to take a little bit of time to get some intuition. The more you do, the faster you'll get that intuition. And then what do? I take them, forces, torque, Fx if needed, you probably will, Fy. Right, cool. All right, so I go forces. So I can do this super fast. I can go, okay, Hx, Hy, Mrg, M, yo-yo, G, which that's not too bad. Okay, fine. Anything else? No, I'm done. That's how fast it is. Let's not confuse these two. All right. I just look up there and my picture tells me I'm not done. I got attention. Okay, fine. Now, I need to get the torque from each of these. And what do they add up to? 0. I'll probably need the horizontal components. What are they going to add up to? 0. And I'll probably need the vertical components, and those are going to add up to 0. The hardest part usually is this, okay? So again, we can use any of our techniques of finding torque from a force, right? So we can have it equal to plus or minus r, f, sine alpha, where those are the magnitudes. We can have plus or minus r perpendicular f, or we can have plus or minus r f perpendicular. Those are new, it's a lot, but do enough that you know all of those and you see all of them, then you've learned, the exercise and you're ready for your engineering statics course or anything else. All right, cool. What's missing? Oh, I don't even know what these means. Okay, this is pretty easy. Usually vertical and horizontal, right? Y, X. That's fine. I need to know my A. So the one thing that I'm missing here is choosing an A. Now, you know if the line of force goes through the axis, you're not going around. You're going through. Okay? So I can pick A anywhere you want. You can even take it here or here. The torque value will be different, but they'll still add to 0. All right, so let me go here. That's usually a good choice. I mean, you could do it here. But the beauty here is the torque from HX, since the line of HX goes through it, is 0. The torque from HY, since the line of it goes through 0. And that's beautiful if you don't want H. It's even beautiful if you want H, because it still makes this nice. You're going to have to go over here, and you're going to get your HX and your HY in these equations here. So, yes, you've gotten rid of maybe what you want, but you're going to include it in a little simpler case over here. So then you go here, and I go, hey, MRG. Well, let me see. Which way am I going to look at it? Well, I can look at the line of the force. I could look at R. R is from the axis to the point of application, because that would be R. Or I can look at R perpendicular, which is the lever arm, which is from the axis, shortest distance to the line of force. And so there's my R perpendicular. And you may well know that, or you may use geometry. This is going to be 90 degrees minus theta, right? And then it's going to be R sine of 90 degrees minus theta. It's great, so that's kind of nice. Or, separately, you could look at the part of mg that's tangential here. So then I go like this, and I go, hey, wait, mg is going, that'd be my F tangential. And they're triangles, they're just triangles. Oh wait, plus or minus. Let me see, this would go this way. I haven't chosen yet. I don't know, I'll call that plus or minus. I kind of like to switch it up, but fine, that's going to be a minus, whatever. This guy is going to be a very identical thing, isn't it? So that's going to be a minus. But what about the tension? All right, the tension's a little tricky, but if you follow the routine, you can see it. So here's the line of force. R is from the axis of rotation to the point of application, so that's always R for my tension, right? I have to be very careful, it looks like R perpendicular. R perpendicular is from the axis of rotation, shortest distance to the line of force. There's R perpendicular. You can use RF, sine of the angle between these lines. You can use F, which is tension, times that, just use geometry. Or you can use the part of torque that is tangential or perpendicular, T perpendicular to R. Any of those will get you the right answer. And by the way, you can see that the torque is positive or negative, or I should say clockwise or counterclockwise. Counterclockwise, good, because these have got to add up to 0. And then you separately notice that that is neither Tx nor Ty. So if you want to do the X and Y part, then you got to go, okay, horizontal, vertical. So that's different. So that's a pretty rich example, I think. And we'll take a look at another example. How much time have we?
You're about done.
About done. Yeah, I think so. I think we're probably all about done right now. So we should look at ladders. Those are classic and good. And then another little cool thing. I think I might set that up in the next one real quick.